Good morning, everyone. I'm Devdatta Kulkarni. I'm the founder of CloudARK, and today I'll be talking to you about Helm and operators. So, little bit about me. Before starting CloudARK, I used to work at Rackspace, where I led the team that built platform as a service for OpenStack. And since then, I've been working developing CloudARK. So, for today's talk, the outline is let's go over quickly what operators are, what is a Helm chart, just to set the stage, then why building Helm charts for operators makes sense. Then I'll talk about some of the analysis that we have done about operators. Amongst them, we have looked at the Helm charts of existing operators. And then I'm going to share with you some guidelines if you are developing operators and what kind of things you should be doing when building Helm charts for operators. And then I'll talk about a few other things around operators and Helm charts, what kind of experience that they enable. Okay, so what is a Kubernetes operator? It has become popular in last year or so. Essentially, a Kubernetes operator is a custom resource and a custom controller that one can add into your in a cluster to run essentially any kind of workflow. And typically these days, operators are being used to manage stateful services like databases on Kubernetes. One of the great things about operators or custom resource definitions is that they are Kubernetes native, so you can use standard things like kubectl to work with these custom resources. You can use Kubernetes native tools like Helm, and they work with namespaces, service accounts, all the nice things that we get with base Kubernetes. There are already like 400 plus GitHub repositories of operators for various kinds of things. So you will find operators for relational, non-relational databases, application workloads, API gateways, and as the picture shows, the main thing about these is the custom resources that an operator introduces. They are at the same level as the standard Kubernetes resources. So like the way we have pod service deployment, we also can have Spark, MySQL, Kafka. So extending the Kubernetes cluster, creating new abstractions by actually extending the cluster and not wrapping things as we used to do in the old days before Kubernetes. So that's the operator and Helm. This is the Helm Summit. So I know all of us understand this, but at a high level, what Helm allows us to do is it allows us to templatize and parameterize Kubernetes artifacts for different environments. We can create through values.yaml different parameterization for a Kubernetes artifact. So that's one. The other thing that Helm allows us to do is essentially order and orchestrate the actual artifact. So there are several hooks that Helm defines, and these can be used for doing that ordering and orchestration. So why develop a Helm chart for operator? If you think about it, an operator is no different than any other Kubernetes artifact, right? You have, in order to run something as an operator, you need to create a pod for it, you need to deploy that pod, you need to grant it certain permissions, define certain service accounts. So, and Helm allows us to distribute and package standard Kubernetes artifacts, and operator just happens to be a Kubernetes artifact. So it makes sense to use a standard package manager like Helm to distribute your operators. The second reason is you can actually use the parameterization and templatization features that Helm provides to customize your operator for different environments. For prod environment, you want an operator to behave in a different manner, whereas when you are developing it, you want it to behave a little bit differently. You can do that straightforward using Helm. So that's awesome. The third reason to stick with using Helm is you don't need to learn about any new spec format for app deployment and the control plane deployment. So if you think about it, operators can be considered as control planes. You are adding new controllers to your cluster. And then the actual Kubernetes artifacts are your applications. So if you use Helm, then for both, then you, as your team, you don't need to learn any new artifact for that. And then as part of Helm charts, you can leverage Kubernetes constructs like labels, annotations, CRD manifests, etc., for, again, doing the control plane deployment and the application deployment. So this is the reason why one should develop Helm charts for operators. So with that in background, we looked at existing GitHub repositories of operators. As I said, there are 400 plus operators in the community. And we selected any repository which has 10 plus stars. And out of that, so 102 turned out to be like that. This was, by the way, done in April of this year. So things might have changed since then. And out of these 102 repositories, we focused on the ones which were written in Go. So one can write operators in any language. Still, the predominant language is Go. So what did we really see in these operator repositories? So the Helm charts for operators were defined by about half of these repositories. Okay, so not everybody out there is still developing Helm charts for operators. The second key takeaway was one of the things that you need to do as part of registering a new API in Kubernetes, a custom resource API, is to define the custom resource definition. So it's like a meta API that you add in your cluster, and then after that you can start using your custom resources. So as part of analysis, what we found was not everyone was defining this CRD, the meta API, in YAML or Helm charts. There were quite a bit of repositories in which these things were getting done in the code itself. Okay, and then the final point was in order to make sure that your custom resources are created in a manner that they are rightly defined and structurally and semantically the properties make sense, you can add these validation rules when you register your custom resource definition meta API. And not everyone was doing that. Okay, so that was at a high level the key takeaway of this analysis. So based on that and having worked with operators, we have come up with these set of guidelines. And in the rest of the talk, I'm going to go through these guidelines. Okay, so at a high level, the guidelines are register CRDs as part of operator Helm chart. There's a special hook CRD install that we recommend that everyone add on their CRDs. Use values.yamls or config-mac for configurables. Define validation rules for CRDs, and then there are additional annotations that I'm going to introduce which help you create your operators in such a way that they can use seamlessly in an ensemble of multiple operators. And we call these as platform as code annotations, and I'll talk about them. So the first guideline is to register CRDs in your operator Helm chart. So what is a CRD? A CRD is the meta API or the custom resource definition YAML that introduces in your cluster the new custom resource. So let's say if you want to create a Spark cluster and Spark as your custom resource, then you need to first define CRD for Spark as part or register and in your cluster. So why should we do this in YAML and not directly do it in the Go code or your operator code? The reason is the CRD object itself has to be done using cluster scope permission. It's a non-namespaced object, so you need to install it with the permissions that have broader surface area than or permission set than what you would do for actually registering the operator pod itself. So separating these two makes sense because CRD installation can be done by someone who has more privileged access to the cluster, someone like a overall administrator, whereas the operator pod deployment can be done per team in different namespaces. So that is the main reason you should separate it out, the two things. Not only that, the other thing that you should do is to define the CRD install Helm Hook as part of your Helm chart. So here's an example of that annotation. And by the way, here is that custom resource definition meta API that you should register. And this is from one of the open source operators. This is a MySQL operator from Press Labs in which they have defined this. So what this hook does is it allows, when you define this and install this particular YAML as part of the Helm chart, what's going to happen is Helm is going to first install this artifact before installing any other thing that might be defined as part of your chart. And that includes creation of the actual custom resources. So in this case, the MySQL backup is the custom resource which you would have defined, let's say, as part of your chart. And if you don't define this annotation, what's going to happen is Helm may try to register and deploy MySQL backup custom resources first, but that will fail. So you don't want to, you want to avoid that. And that's why defining this annotation is essential. So the third guideline is just calling out this fact that because you are now developing your Helm chart, it's possible for you to actually customize your operator deployment for different environments. There are two ways you can do it. Values.yaml is a very simple way to customize an operator. Let's say just changing the image. If you have a MySQL operator and you want to use different Docker images in different environments, values.yaml is a very good way to do that. But let's say if you have much more customization, and one of the customers that we are working with, the way they wanted to customize was the operator had to behave completely differently in certain environments for their customers. So new plugins had to be installed, and a plugin installation required more things like what path to install that plugin, and this was an operator for the Moodle e-learning software. So for that, values.yaml is not sufficient, and the way still you can customize your operator is by using config maps, again a standard Kubernetes artifact. If you can define these config maps ahead of time, then you can package them as part of your Helm chart, and that way you can customize your operator. The fourth guideline is to make sure that your custom resources are created in such a way that they are semantically, structurally, the way you expect them to be. And part of that, it means to define these CRD validation rules. This is now part of Kubernetes Upstream. I believe from 1.15 onwards, this is possible. So what you need to do is, as part of this custom resource definition, again, remember this is the meta API, make sure that you add these validations, and these validations are for the custom resource that the user is going to create. So for the Postgres custom resource here, I'm saying, defining the validation rule that there can be a spec property of databases which is an array of type string, and similarly user. So any sort of, if you are an operator developer, you want to think ahead and create these validations ahead of time, include them as part of your CRD definition, and then once you package this as part of your Helm chart, it will make sure that custom resources are created in the way that you want them to be created. So this was the fourth guideline. Now for the final guideline, this is something that new that we at CloudARK are developing, and I want to talk about the rest of the talk on that, which is essentially we recommend that you add these new annotations. We call them platform as code annotations. There are two annotations that we have defined. One is the usage annotation, and another is the composition annotation. And these annotations are to be added similar to the CRD install hook directly on the custom resource definition. And what these annotations do is the usage annotation allows you as an operator developer to package any kind of information that is beyond the spec properties, but which is needed by your users to consume that custom resource. And I'll talk about an example of how we use this. So usage annotation, the value of that is just a name of the config map. So in this case, this is the name of the config map and the key in that config map. And so that's the usage annotation. The contents of that config map can be anything that you want as an operator developer to include as part of like the information that your user needs to know about your operator. The second annotation is the composition annotation, and this annotation is the values of that are all the underlying resources that your operator is going to create as part of instantiating a custom resource. So what I mean by that is, in this case, the custom resource that this operator manages is the Moodle custom resource. And as part of creating a Moodle instance, it's going to essentially create a deployment, a service, persistent volume, claim, secret, ingress, and so on. So any and all custom resources that your operator is going to create, just list them out as part of the composition annotation. Okay? And how are these useful? These annotations are useful in the following way. So before jumping and thinking about how they are useful, I would like to talk about application developers and how they are using custom resources. So one of the things that is different with Kubernetes than the traditional cloud systems is that you can extend the control plane of Kubernetes by adding new operators. And that makes the challenge of creating declarative application stacks little bit different than traditional infrastructure as code systems like Terraform or CloudFormation, because in those systems, the underlying API is not going to change ever. It's known ahead of time. That's never going to change. With Kubernetes, that's not the case. You have these operators and custom resources that can be installed at any time on any cluster. So that's one aspect how Kubernetes is different. The second aspect, if you think about the custom resources that we create, they are essentially embedding some higher level actions. So let's say if I am using a custom resource for MySQL, then there are only certain things that that custom resource is declarative going to expose. So things like take a backup or instantiate a new database in a certain manner. So compare this with our traditional platform as a service systems like Heroku and Elastic Beanstalk. They were providing very constrained manner of deploying your applications. So these custom resources are defining essentially that kind of platform experience in a declarative manner. So the ensemble of custom and inbuilt resources that one now creates when operators are involved, the declarative application stacks, it's natural to think about these as your platform definitions as code. So as an application developer, when they are working with custom resources, the challenges that arise are, how do I discover what all custom resources exist in my cluster, how do I use these custom resources, and so on. So that's one aspect, the discovery challenge. And the other challenge is to how to bind these custom resources together. So is there, in Kubernetes, there are things like names and labels, label selectors. Those are enough to sort of bind different resources together. With custom resources, is that enough, or is something more is needed? That's the question. And so if you look at the existing tools, so we have Helm, we have base Kubernetes itself, and what kind of support that's possible currently in these tools. Kubernetes provides a way for us to just find out more about spec properties of custom resources through explain. And as far as binding is concerned, Helm, Kubernetes, both more focus on the statically defined information. So if you look at values.yaml as well, it's, or even customized for that matter, what you have is values that are defined and which you can change, but these values are not going to change based on what exists in the in a cluster. So those are the gaps, and what those are the gaps that need to be filled for creating these application stacks, the platform stacks declaratively. For that, we have been developing the Q+ API add-on, which fills these gaps. Q+ is meant to complement existing tools. So it complements Helm, it complements Customize, and it consists of sort of 3 independent entities. There is an aggregated API server, which helps with discovery. There is a mutating webhook, which helps with binding resolution using runtime information. And then there's a platform stack CRD as well, which just ensures that the ordering between custom resources is maintained. So essentially, Q+ for discovery, what Q+ provides is new API endpoints that are accessible directly through kubectl to find runtime and static information. And for binding, we provide value-based, runtime value-based resolution, and I'll show you an example of that. Okay, so in order to explain this in a more detail, this is the sample scenario I'm going to use. Assume that we have an Kubernetes cluster in which 2 operators are installed. One operator is the MySQL cluster from Press Labs, which I mentioned earlier. The other operator is a Moodle operator, which allows you to essentially create deploy multiple Moodle instances. And the way we are going to create a stack is to essentially in the Moodle custom resource, I'm going to use the MySQL cluster custom resource. And the way this association is going to happen is the underlying service that the MySQL cluster creates, that's the name of that needs to be passed in as part of the Moodle custom resource instance. So here, this is the name that I'm passing in. The question is, this is something that I've defined, but how does an application developer get to know that this is the name I need to pass in, and can that binding be done, resolved automatically? So for the application developer, as I said, we introduced 2 endpoints. There is a man endpoint, which is essentially a way for you to get man page kind of information for the custom resource. And the other endpoint is the composition endpoint, which allows you to get a composition tree of a custom resource. So here's an example of using the composition endpoint on the MySQL cluster instance. And this is using that annotation that I showed you earlier, the composition annotation. Our API server knows what all component objects are created. So behind the scene, it is parsing following the owner reference tree and building out this particular tree. And based on this output, I can find out as an application developer that, yeah, there are multiple services. One of the services whose name is MySQL master. And then based on the man page information, I can go and choose to define this in my YAML. So that is good, but then I want to do this automatically. So for that, what we do is, instead of having me to do this manually, we define these binding functions. And one of the functions is import value. These are function definitions. The structure is inspired from CloudFormation. So how do we use these import value functions? It's like this. So now, instead of hard coding the value of the service object, I'm going to define that the value should be imported. And what value I need to import is the kind name is MySQL cluster. In the default namespace, the cluster1 is the actual name of the MySQL cluster instance. Of that, the sub resource I want to use is the service sub resource. And if there are multiple services, I want to filter that based on if the name contains the string master in it. So essentially, by defining it this way, what I'm doing is I'm creating dissociation between a definition of the Moodle custom resource and in any environment where it may get installed. I can, without changing the YAML spec, I will be able to deploy the same thing in other environment as well. And the resolution in that will happen at runtime based on whatever the MySQL cluster service is created in that particular cluster. So in summary, create Helm charts for your operators and use the guidelines that I talked about. The guidelines here are subset of, there are additional guidelines, and I have linked to those guidelines. These are all open source, by the way. So you can take a look at it, all the guidelines that we have around operator and custom resource development. These ones that I talked were specifically around Helm, but there are others that should be helpful. Then there is this notion of declarative application management in Kubernetes, and our view is that with custom resources, declarative application management needs special attention, especially if you are using multiple operators in a cluster. Help your application developers to streamline the discovery and binding of those custom resources by adding platform as code annotations. And those annotations actually will make sense only if you also have the Q+ API add-on installed in your cluster. So it's open source as well. Install it. You can use it alongside Helm. It doesn't replace Helm or customize. You can use all these tools together. And that's how you will be able to then start building your platform as code stacks. Thank you. I think we have some time for questions.
So deploying
Yeah.
Q+, how involved is that? Is that just like another?
Yeah, it's yeah, that's a great question. So the question is, how involved is deploying Q+ itself? So for deploying Q+, it's we are in the process of building a Helm chart for doing that. It's not there yet, but yeah, it's not involved at all. You would need the privileges for cluster admin to do that because it involves installing the aggregated API server. But yeah, apart from that, it's like deploying any other Kubernetes artifact. Yes?
So you mentioned the hook of installing the custom resource definition.
Yes.
So what if, like, instead of the hook, the custom resource definition is in an entirely different construct? Is it better or worse?
That's a great question. So the question was, instead of having the hook defined like this, can you just have a separate Helm chart for just installing the custom resource definition? You could do that. You need to ensure that that Helm chart gets deployed first. Now the question is that ordering, are you going to ensure from some outside means, or so the hook helps you just avoid all of that. But yeah, you could do that. All right, thank you. I'll be around, so if you need anything, we can discuss more. Thank you.